All right, so we're going to pick up where we left off in the last video. We're working on this example. Part A, we're computing the slopes of secant lines corresponding to the intervals t, or the intervals of t 20 to 30 and 30 to 40. And then we're going to interpret those results. So let's start with part A. And what we're looking for is the slope of a secant line, which is the way that we interpret slope is the change in your dependent variable over the change in your independent variable. So let's say on this interval, 20 to 30, our slope, m, is equal to what? Well, the dependent variable is given by our steps. So we think of the number of steps that this student has taken as being a function of t, a function of time that has passed in minutes. So looking on the interval from 20 to 30 here, what was the change in the number of steps? Well, she ended up at 6,536 steps, and we're going to subtract the number of steps she had by 20 minutes, 5,622, and that'll give us the total number of steps she took from 20 minutes to 30 minutes, that difference. We divide that by the change in time. So change in steps over the change in time. 30 minutes minus 20 minutes, okay? That's how we would compute the slope of that secant line. This you can do by hand or in a calculator. It's fairly easy. This comes out to 91.4. Okay, so that's the first slope. On the next interval, 30 to 40, the slope is going to be the change in the number of steps, which this time is 7,398. 7,398 minus 6,536 over the change in time, 40 minus 30. And in this case, again, go to a calculator or something and work this out. We get 86.2. Okay? So we've computed these slopes, but now we want to come up with an interpretation of what they represent. And again, remember, the slope of a line represents a rate of change, and it helps to think of the units here. So in each of these cases, when I evaluated slope, we did the change in the number of steps divided by the change in the amount of time, which was measured in minutes. So these are going to have units of steps per minute. In fact, even though it just asked for the slope, I can write that in here, steps per minute. Okay? So both slopes represent, now before I just say her rate of change, we need to be careful with this because if you notice, she took more steps per minute in this first interval from 20 to 30 than she did in this second interval. So we already see, because these values are different, that she's not maintaining a constant rate of speed or a constant rate of walking, steps per minute. And in fact, because we're looking at 10-minute intervals here, we don't know if she's speeding up or slowing down or a mixture of those over the course of both of these intervals. So this doesn't really represent it's not enough to just say that this is her rate of steps per minute over this interval, because that rate can change over the course of those 10 minutes. Instead, what we would say is it's an average rate of change. If you look at the totality of her rate of change over the course of these 10 minutes, it will average out to 91.4. So we need to make sure we're using that term, average rate of change. Both slopes represent the average rate of steps per minute over their respective intervals. Okay, on to part B. What are we doing in part B? Let's come back up here so we can read it. It says, use the results of part A to approximate the slope of the I shouldn't say the slope of the slope. It should just say the slope of the tangent line to the curve given by this function at t equals 30. And it's asking what does this slope represent. So to get a sense of how we're supposed to do this, even though we're given a finite number of points of data here, this would be a function that we could record more steps. You know, we could look at 1 minute intervals or 1 second intervals or microsecond intervals. We can record much more data than what's given to us here. And what this suggests is that there is a graph that would correspond to this function of t. So I don't know what that graph looks like because I'm given very minimal data here. But let's just suppose, you know, it had some kind of a curve to it. Again, we have no idea exactly what it looks like, but this is just meant to give us an idea, you know, a general idea of what we're looking at. So 20, 30, 40. Here's the intervals that we just found the average rates of change over. And the first slope that I found up here, this 91.4, would correspond, and actually this is already, I can already tell this is an inaccurate graph, but that's okay. It would represent the slope of that secant line right there, okay? Then if I were to look at the secant line that the second slope here represents, that might look something like this, right? Now the idea here is that these two slopes are different, but we're using them to try and approximate the slope of this tangent line. And you notice the way that I drew this graph, which is not correct, but it conveys, you know, the right idea, is that my tangent line right here kind of looks like it's steepness-wise in between my two secant lines. I have one secant line that has a greater slope, one secant line that has a shallower slope. So one way of approximating this tangent line logically would be to average the two slopes that we have here. And that's really the best that we can do with the information that we have. So if I wanted to come up with that, I would say that my approximation at t equals 30 is the mean or the average of the two slopes that I just found. That's 91.4 plus 86.2 divided by 2. And this works out to 88.8. And again, that would be in steps per minute. It's saying, what does this slope represent? Well, now, instead of finding the slope of a line over an interval, which we said when it's over an interval like this, we have to think of that as an average rate of change. Now we're trying to approximate our rate of change at an instant in time. So what does that mean? Well, this slope represents the rate of steps per minute at the exact instant when t equals 30. Okay, so we're no longer looking at average rates of change over an interval of time. I'm looking at the instantaneous, is the word that we use, instantaneous rate of change in steps per minute at the exact moment that t equals 30. Okay, let's go ahead and move on from this example here. So I want to examine that idea a little bit more thoroughly. Okay, so as I kind of say up here, the previous example, part B of that previous example, is giving us some insight into the reason why we care about these tangent lines, in particular these slopes of these tangent lines. Those slopes represent rates of change. And again, if we're looking at the the rate of change over an interval, that would be an average rate of change. But if we're looking at the rate of change at an instant, we call that instantaneous rate of change. I'll give definitions for those at the bottom of this page. The instantaneous rate of change it can only be found if we can find the slope of the corresponding tangent line. Okay, and this graph here kind of gives you an interpretation of slope using a notation that you need to know for this class. So here we have a red line, and you can compute the slope of this line by picking any 2 points on this line and taking the ratio of the change in the y coordinates of those points over the change in the x coordinates of those points. And the word change in calculus we represent by this Greek letter delta, which we read as delta y or delta x, or the change in y, the change in x. That's what that delta represents. Okay, so by computing slope then, our slope formula would tell us that m, our slope, is equal to delta y over delta x. But this quotient is a rate of change, like we said before, and the units it would take on are the units of y over the units of x. So in our previous example, we had steps and minutes, and so the rate of change was measured in steps per minute. Okay, I already talked about this, so I'm not gonna read this through, but this is basically just saying that the average rate of change is represented by the slope of a secant line. Like we've said, instantaneous rate of change is represented by the slope of a tangent line. This first thing we're able to find with algebra. This second thing we need calculus in order to find. So the rates of change come in many, many different forms depending on the units that we're using, the kind of applications that they appear in. And to kind of spend more time exploring this idea, probably the easiest application in which to think about rates of change is that of velocity and position in particular. So for this, we're going to set up kind of a convention that we use when we talk about velocity. What I want to do is imagine a number line with positive and negative real numbers and 0. And we want to imagine a little particle or a point that lives on this number line. And that particle is going to start at the number 0. So I'm thinking of 0 as representing its initial position, the starting point of that particle. The particle is allowed to move, but it can only move in such a way that keeps it on the number line. So it can move to the right and it can move to the left, and that's it. It can't move up or down, okay? So if we kind of imagine that, there's a couple of functions that we can define that are relevant to this scenario here. So we can talk about, first of all, a position function. Again, I'm talking about this particle moving. So in particular, if it's moving, then a variable representing time would be relevant here. It's moving over the course of time. So we're going to define a function which we're going to call s of t. And this is what we call a position function. It's also frequently called the displacement function. And the purpose of this function is to tell me exactly what position the particle is at on my number line at some given time t. Okay, so, so just to give you some examples of values you could get from this position function. Because we're saying that the particle is starting at the position 0 at time 0, I could say s of 0 equals 0. That s of 0 indicates the initial position of that particle. Let's suppose that after 4 units of time, which could be seconds, minutes, hours, whatever, the particle has moved to 3 on our number line. So it's moved to the right from 0 to 3. Then I can write s of 4 equals 3. After 4 units of time, we are at the position 3. Then suppose after 10 units of time, the particle moves towards the left and it ends up at the position of -1. I could write s of 10 equals -1. That's the position we are at 10 units of time after starting this movement. Okay? And so it's important to note here that positive values of s, positive positions, are to the right of our starting point, and negative positions or negative values corresponding to positions are to the left of our starting point. And this is a matter of convention. that we think of the right as being positive and the left as being negative. That doesn't necessarily have to be the case. It usually will be, but we're allowed to change the orientation of this thing, of this number line, if it suits the problem that we're using it for. So if it makes sense in a problem to define left to be positive and right to be negative, we can do that, but you're going to have to explain that. If you're not, it's generally implied that right is positive, left is negative. Okay, now because we're talking about movement here, we can naturally talk about the concept of speed. And speed is a rate of change in distance over time. But there's something about speed that's insufficient for describing this situation. Speed, as we understand it, can only be a non-negative quantity. We can't make sense of negative speed. However, there's a related concept which we call velocity. We're going to give a definition for that here. And velocity can be negative. It can be positive, it can be zero, it can be any real number. And velocity also tells us the speed, but whether that velocity is positive or negative indicates which direction that particle is moving. So let's kind of make a little bit more sense of that down here. And before I do that, I did want to mention this as well. The number line on the previous page was horizontal, but there's oftentimes a good reason to think of our number line as being vertical. We're going to see, I think in an example towards the end here, that a place where we could use this concept is in dealing with a falling object, the rate of change or the rate of velocity of an object in free fall. So if you're dropping an object, it's going to be dropping vertically downwards, and it makes sense to use a vertical number line to model that. Okay, so in that kind of case, we oftentimes think of down as being the positive direction and up as being the negative direction. And that's a little bit counterintuitive, because if you're thinking about it in terms of the Cartesian plane, our vertical axis is the y-axis, and on the y-axis, positive is up and negative is down, and we're kind of reversing this here. Once again, it doesn't have to be represented this way. You can have up be positive and down be negative, but because a problem involving free fall is going to have an object moving downward, it's oftentimes more convenient in those cases to have the downward direction be represented by the positive numbers. Okay, so we'll encounter that again very soon, but let's look at velocity in a little bit more detail here. How do we define velocity? Well, velocity is going to be very closely related to speed, like we said. It's a rate of change, and in particular, we're going to denote velocity with v. It's going to represent the rate of change in position over the corresponding rate of change in time. Okay, so if a particle moves from point A to point B over the course of t units of time, then the total displacement of that particle going from point A to point B divided by that rate of time is going to give us that velocity. Now, this rate of change in position can be negative, and we'll see why that is soon. But if that's the case, time is always going to be measured as a positive quantity, so a negative over a positive would give us a negative. In those cases, velocity can be negative. Okay? Now, with velocity being a rate of change, we think of it in the same way that we think of other rates of change. And on the previously, we talked about the difference between an average rate of change and an instantaneous rate of change. An average rate of change is measured over an interval, while an instantaneous rate of change is measured at an exact instant in time. And so that applies to velocity as well. Average velocity is going to be what the average velocity would have been over an interval of time. Instantaneous velocity is the exact velocity at an exact instant in time. Okay? I feel like I just said the same thing like 3 times in a row, just with different words, but that's fine. So in the next video, we'll take a look at some examples using this concept.